Zen is a hypervisor using a microkernel design, providing services that allow multiple computer operating systems to execute on the same computer hardware concurrently. The University of Cambridge Computer Laboratory developed the first versions of Zen. The Zen community develops and maintains Zen as free and open source software, subject to the requirements of the GNU General Public License, version 2. Zen is currently available for the IA32, x86-64 and ARM instruction sets. Software architecture: Zen runs in a more privileged CPU state than any other software on the machine. Responsibilities of the hypervisor include memory management and CPU scheduling of all virtual machines, and for launching the most privileged domain, the only virtual machine which by default has direct access to hardware. From the DOMO, the hypervisor can be managed and unprivileged domains can be launched. The DOMO domain is typically a version of Linux, or BSD. User domains may either be traditional operating systems, such as Microsoft Windows, under which privileged instructions are provided by hardware virtualization instructions, or Paravirtualized operating system, whereby the operating system is aware that it is running inside a virtual machine, and so makes hypercalls directly, rather than issuing privileged instructions. Zen boots from a bootloader such as GNU Grub, and then usually loads a Paravirtualized host operating system into the host domain. History: Zen originated as a research project at the University of Cambridge, led by Ian Pratt, senior lecturer at Cambridge, who co-founded Zen Source, Incorporated with Simon Crosby, also of Cambridge University. The first public release of Zen was made in 2003. Zen has been supported originally by Zen Source Incorporated, and since the acquisition of Zen Source by Citrix in October 2007. This organization supports the development of the free software project and also sells enterprise versions of the software. On October 22, 2007, Citrix Systems completed its acquisition of Zen Source, and the Zen project moved to http://www.zen.org/. This move had started sometime previously, and made public the existence of the Zen Project Advisory Board, which had members from Citrix, IBM, Intel, Hewlett-Packard, Novell, Red Hat, Sun Microsystems and Oracle. The Zen Advisory Board advises the Zen project leader and is responsible for the Zen trademark, which Citrix has freely licensed to all vendors and projects that implement the Zen hypervisor. Citrix has also used the Zen brand itself for some proprietary products unrelated to Zen, including at least Zen App and Zen Desktop. On April 15, 2013, it was announced that the Zen project was moved under the auspices of the Linux Foundation as a collaborative project. The Linux Foundation launched a new trademark for Zen project to differentiate the project from any commercial use of the older Zen trademark. A new community website was launched at http://xenproject.org/. As part of the transfer, project members at the time of the announcement included Amazon, AMD, Bromium, CA Technologies, Caltar, Cisco, Citrix, Google, Intel, Oracle, Samsung, and Verizon. The Zen problem itself is self-governing. Release history for Zen, Zen and Linux distributions and Linux upstream. Since version 3.0 of the Linux kernel, Zen support for DOMO and DOMU exists in the mainline kernel. Uses: Internet hosting service companies use hypervisors to provide virtual private servers. Amazon EC2, IBM SoftLayer, Liquid Web, Fujitsu Global Cloud Platform, Linode, Orion VM and Rackspace Cloud use Zen as the primary VM hypervisor for their product offerings. Virtual machine monitors also often operate on mainframes and large servers running IBM, HP, and other systems. Server virtualization can provide benefits such as consolidation leading to increased utilization, rapid provisioning, dynamic fault tolerance against software failures, hardware fault tolerance, the ability to securely separate virtual operating systems, the ability to support legacy software as well as new OS instances on the same computer. Zen's support for virtual machine live migration from one host to another allows workload balancing and the avoidance of downtime. Virtualization also has benefits when working on development. Running the new system as a guest avoids the need to reboot the physical computer whenever a bug occurs. Sandboxed guest systems can also help in computer security research, allowing study of the effects of some virus or worm without the possibility of compromising the host system. Finally, hardware appliance vendors may decide to ship their appliance running several guest systems, so as to be able to execute various pieces of software that require different operating systems. Technology, types of virtualization. Zen supports two different approaches to running the guest operating system. The choice of approach is up to the Zen hosting system administrator. Paravirtualization, modified guests. Zen supports a form of virtualization known as paravirtualization, in which guests run a modified operating system. The guests are modified to use a special hypercall ABI, instead of certain architectural features. Through paravirtualization, Zen can achieve high performance even on its host architecture, which is a reputation for non-cooperation with traditional virtualization techniques. Zen can run paravirtualized guests even on CPUs without any explicit support for virtualization. Paravirtualization avoids the need to emulate a full set of hardware and firmware services, which makes a PV system simpler to manage and reduces the attack surface exposed to potentially malicious guests. On 32-bit x86, the Zen host kernel code runs in Ring 0, while the hosted domains run in Ring 1 and Ring 3. Hardware-assisted virtualization, allowing for unmodified guests. CPUs that support virtualization make it possible to support unmodified guests, including proprietary operating systems. This is known as hardware-assisted virtualization, however in Zen this is known as hardware virtual machine. Hvm extensions provide additional execution modes, with an explicit distinction between the most privileged modes used by the hypervisor with access to the real hardware and the less privileged modes used by guest kernels and applications with hardware accesses under complete control of the hypervisor. Both Intel and AMD have contributed modifications to Zen to support their respective Intel VTX and AMD V architecture extensions. Support for ARM v7a and v8a virtualization extensions came with Zen 4.3. Hvm extensions also often offer new instructions to support direct calls by a paravirtualized guest driver into the hypervisor, typically used for I/O or other operations needing high performance. These allow Hvm guests with suitable minor modifications to gain many of the performance benefits of paravirtualized I/O. In current versions of Zen, only fully virtualized Hvm guests can make use of hardware support for multiple independent levels of memory protection and paging. As a result, for some workloads, Hvm guests with PV drivers provide better performance than pure PV guests. Zen Hvm has device emulation based on the QEMU project to provide I/O virtualization to the virtual machines. The system emulates hardware via a patched QEMU device manager daemon running as a backend in DOM-O. This means that the virtualized machines see an emulated version of a fairly basic PC. In a performance-critical environment, PV on Hvm disk and network drivers are used during normal guest operation, so that the emulated PC hardware is mostly used for booting. Virtual machine migration. Administrators can migrate Zen virtual machines between physical hosts across a LAN without loss of availability. During this procedure, the LAN iteratively copies the memory of the virtual machine to the destination without stopping its execution. The process requires a stoppage of around 60 €300 ms to perform final synchronization before the virtual machine begins executing at its final destination, providing an illusion of seamless migration. Similar technology can serve to suspend running virtual machines to disk, freezing their running state for resumption at a later date. Target processors. The Zen hypervisor has been ported to a number of processor families. Intel, IA32, IA64, x86-64. PowerPC, previously supported under the XENP-PC project, no longer active after Zen 3.2. ARM, previously supported under the Zen ARM project for older versions of ARM without virtualization extensions, such as the Cortex-A9, currently supported since Zen 4.3 for newer versions of the ARM with virtualization extensions, such as the Cortex-A15. MIPS, XLP832 experimental port. Scalability, Zen can scale to 4095 physical CPUs, 256 vCPUs per HVM guest, 512 vCPUs per PV guest, 16 TB of RAM per host, and up to 1 TB of RAM per HVM guest or 512 GB of RAM per PV guest. Hosts, Zen can be shipped in a dedicated virtualization platform, such as Citrix Zen Server Enterprise Edition. Alternatively, Zen is distributed as an optional configuration of many standard operating systems. Zen is available for undistributed with, Alpine Linux offers a minimal DOM system that can be run from removable media, like USB sticks. KBS for desktop usage, OpenSUSE 10x to 12x. Only 64-bit hosts are supported since 12.1, SUSE Linux Enterprise Server, Sun Microsystems Solaris, Debian GNU Linux and many of its derivatives, Ubuntu 12.04 Precise Pangolin, and later releases. Also 8.04 Hardy Heron, but no DOM-capable kernel in 8.10 Intrepid Ibex until 12.04, Gentoo and Arch Linux both have packages available to support Zen. Open Solaris-based distributions can function as DOM-O and DOM-U from Nevada Build 75 onwards. NetBSD 3X includes host support for Zen 2, with host support for Zen 3.0 available from NetBSD 4.0. Untitled Corporate Server, Mageia, guests, Unix-like systems as guests. Guest systems can run fully virtualized or paravirtualized. Most operating systems which can run on PC can run as a Zen HVM guest. Additionally, the following systems have patches allowing them to operate as paravirtualized Zen guests: Linux, Paravirtualization integrated in February 6, 2023. Patches for other versions exist: MINIX, Plan 9 from Bell Labs, NetBSD, FreeBSD, Open Solaris, NetWare, Numac, Ozone, Microsoft Windows systems as guests. Zen version 3.0 introduced the capability to run Microsoft Windows as a guest operating system unmodified if the host machine's processor supports hardware virtualization provided by Intel VTX or AMD. During the development of Zen 1X, Microsoft Research, along with the University of Cambridge Operating System Group, developed a port of Windows XP to Zen made possible by Microsoft's academic licensing program. The terms of this license do not allow the publication of this port, although documentation of the experience appears in the original Zen SOSP paper. James Harper and the Zen open source community have started developing GPL paravirtualization drivers for Windows. These provide front-end drivers for the Zen block and network devices, and allow much higher disk and network performance for Windows systems running in HVM mode. Without these drivers, all disk and network traffic has to be processed through QEMUDM. Zen Management Consoles. Third-party developers have built a number of tools to facilitate the common tasks of administering a Zen host, such as configuring, starting, monitoring and stopping of Zen guests. Examples include the web-based Hyper-VM, web-based Convite, the Open Nebula Cloud Management Toolkit, on OpenSUSE ST Invite Man offer graphical VM management, UCS Virtual Machine Manager, default component of Untitled Corporate Server. Web-based Zen Orchestra, Novell's PlateSpin Orchestrate also manages Zen virtual machines for Zen shipping and SUSE Linux Enterprise Server. Commercial versions of Zen, Citrix Zen Server, Oracle VM, SunX VM, Virtual Iron, Thincy Corporation, Huawei Fusion Sphere. The Zen hypervisor is covered by the GNU General Public License, so all of these versions contain a core of free software with source code. However, many of them contain proprietary additions. See also: kernel-based virtual machine, comparison of platform virtual machines, virtual disk image, OpenStack, CloudStack, references. Further reading: Paul Venezia Virtualization Shootout, Citrix, Microsoft, Red Hat, and BMW ARE. The leading server virtualization contenders tackle InfoWorld's Ultimate Virtualization Challenge, InfoWorld, external links, official website, archivedzn.org page, official Citrix product site, step-by-step installation instructions for Xen, with a DOM-U capable of running Windows XP SP3 and React OS, University of Cambridge research page for Xen, University of Cambridge, Technical Report No. 553, January 2003. Early report outlining the architecture of Xen. Xen Guide by Tapas Mishra, Unified Sessions Manager, an unofficial Xen configuration file creator.